Okay, hello everyone. How did your practice problem go? Do you have any questions about them? Do you have the chance to look at them? Anyone? Okay, your homework that you guys know that your homework is on Blackboard, I meant on Brightspace, and look at it. If you have questions, you can ask me on Wednesday, and it's going to be due a Monday. It means a week from today. Okay, so do you have any questions before I get going? Okay, so let me make, I graded your homework. As you guys know, your homework is on Brightspace, the solution, and I will put, your grade, and I will put the solution on Brightspace tonight. I already wrote it. One question that stood out for a lot of you is the following. So it was on, I will just write it up and discuss a little bit. It was on number 6, I guess, and the question is, how many lists? So it was how many lists of length 6. So we have 6, 1, 2, 3, 4, 5, 6. Link that had the following question. Okay, that had the following property, contains the letter A and B. Contain the letters A and B, and repeat it. Okay. So this was the question. So we want all the string that contains the letter A and B, and the letters can be repeated. So how can we do this problem? Okay, we're gonna look at the complement. So we're gonna introduce the universe, which is all possible list. With repeating, everything is repeating. So we're gonna look at the complement or the subtraction rule. And now my question is, what should I subtract from U to get all the letters containing A and B? So we get all string that contain, but I'll write it clearer. So if I take all string that contain A and B. So if I take the complement, it means it's the universe, but what shall I take from it? How can a string not have A and B? Back to you. How can a string not have A and B? Because if you want to use the complement, I have to see, okay, what's left over? What should go here? Subtract including A, including B, and including A and B. So that's a possibility. So Nick suggesting take away, so it's all string that no, I'm not following, Nick. Subtract string including A, including B, but I want all those that contain A and B. How can I subtract those that include A? Not include, yeah. All strings that do not contain A and do not include B and do not include A and B. But strings that do not contain A, I'm trying to rip it apart. So do you want those to contain B or not to contain B? So subtract string not including A or not including B. So let me fix next scenario. How can a string not have A and B? A string cannot have A and B if it doesn't have A or it doesn't have B. I repeat, how can a string not have both? It either doesn't have A or it doesn't have B. That's how it's to complement is, because if you think about it, let me take those that contain A, those contain A, and this one, those that contain B. If I don't want them, so I'm looking at the string that don't contain both, so I'm going to avoid this, means everything else. Mean they either A is not in them by De Morgan's law or do not contain B. So it means the universe, so the cardinality now is the cardinality of that. It means the cardinality of this minus the string that don't contain A or they don't contain B. What's their cardinality? It's those that do not contain A. Plus, you don't have to write because the solution will be up there. Plus those that do not contain B minus those that contain both A, do not contain A and B, minus those that do not contain A and B. A and B. So I repeat, all the things that contain A and B. What's the complement? It means what's left. Either they don't contain A or they don't contain B. If a string doesn't contain A or doesn't contain B, it means it doesn't contain both of them. So that's really what the complement. And now how can I find the cardinality of the string that don't contain A or don't contain B? Since I have a or, I have to find those that don't contain A plus those that don't contain B, but I have to take away from them those that don't contain A and B. Now I have the whole picture. Those, my universe, it's links of 6, and it was 20, we have 26 alphabet to the power 6, minus, do not contain A, I'm fine, I have 25 left to the power 6. Do not contain B, I have 25 to the power 6. But then I have to take what's in common. It means those that contain both of them, which would leave me with that. Okay, that's the problem that most of you had difficulties with. The rest was, every student had their own problem, but this was across the board. Okay, please ask questions before I move on. I hate to move on without you asking questions. Okay, tonight I will put the solution out, and at the same time I will put the rubric so you guys know how I am taking away points, which will become clearer. I don't do it, I do it like I usually grade over like a high number, like 50 or 53, but then I prorate it to 20. So it's not, so I put the rubric so you guys will understand what we're doing.
Professor,
right. Question?
I was going to ask, can I see the answer again for the
I'm going to put on Blackboard, on Brightspace.
Okay.
Solution. Okay?
Mm-hmm.
The solution to the whole homework will be on Brightspace tonight. I already wrote it, but I just have to scan it in. All right? And if you don't understand, you can ask me again. All right? Anybody else? Okay, so today I urge you to do the problem from 4.7 if you guys haven't, because they will help you a lot to do the homework as well. So today we go back to logic, and basically we're going to be working with proofs and logic and set theory and function almost at the end of the semester. So today we're going to start chapter 7 and quantified statement. All right. So far when we did the logic part, we took very simple statement. I mean, really simple. Okay, I said, let's consider the statement 1 + 1 = 2. You know, or let us consider the statement, I don't know, 2 bigger than 3. Very, very basic statement. But of course, we know that in math, you know, those statements don't carry us far at all. And now we have to start introducing things that, well, there is a variable. So if I take the following sentence, x bigger than 2, is this a statement? Remember, a statement is a sentence, it's true or false. So if I take something like that, x bigger than 2, is this a statement? Yes or no? Is this a statement? It means, is this true? Is this false? What can you say? I want answers. Or I'll start being mean and I will ask specific student. My question, is this a statement? Remember, a statement is a sentence which is true or false, but not both. If I tell you x bigger than 2, yes, it is. If you say yes, you give me if it's true or false. Not a statement, absolutely. A statement is a sentence which is true or false. Since you have no idea what x is, so you cannot tell me whether it's true or false. Exactly. All right, so a statement is something which is, there is nothing, there is no ambiguity in it, either false or true, nothing in between. This I know nothing about because I don't know what x is. So that's not a statement. So, and we know that, you know, we're going to be working with statements like that, with sentences like that. So this is going to trigger our first definition of something called predicate. Okay, so we're working with chapter 7 in the book, and I'm covering 7.1 and 7.2 almost together. No, 7.1, 7.3 together. So first, what's a predicate? A predicate in math, because you guys see the word predicate in English, I'm sure. A predicate in math is a sentence that contains a variable, like the one I gave you. So it's a sentence that has a variable, like x bigger than 2, such that whenever x is replaced by a specific value, this sentence becomes a statement. Okay, so for us, a predicate is just a sentence that has a variable. It's not true or it's not false because it has a variable in it. But when the variable takes a specific value, this sentence has to become a statement. So if I take this p of x, the statement x bigger than 2, that's a predicate. It's not true, it's not false. And the way we going to denote a predicate by this way, p of x. That's not a function. I'm not telling you f of x equal. This means that this p of x stands for the statement x bigger than 2. So no, for the sentence. That's a predicate. Now, if I assign a value to this predicate, suppose I put 1 in it, this would read 1 bigger than 2, and this is definitely a statement because this is false. Okay, if I take p of 3, this read 3 bigger than 2, that's a true statement. So the predicate will actually depend on the value of x. Sometimes it's true and sometimes it's false. Okay, now whenever we have a predicate, since there is a variable, I have to tell you usually where this variable takes its value. So we will talk about the domain of a predicate. So the domain will be all the values you wish to allow the variable x to take. And it's usually given to you. So since there is a variable involved, it means I have to tell you what is this x. Okay, so that's what we call the domain of the predicate. The domain are all the value for which the variable x takes its value, and usually it's given to us. And what's the importance of the domain? The domain plays a very important role. So suppose I take the sentence or the predicate p of x, for example, I don't know, x squared larger or equal to x. Okay, bigger or equal to x. And I take for domain all the positive integers. So the domain is all the positive integers, which means, let me be very precise, 1, 2, 3, 4, and etc. That's really the domain. And now I ask you the following question. Is my statement true? Is P of X true? But I have to tell you what I mean. For all X in the domain, what do I mean by that? It means if I plug in any X in my domain, 1, 2, 3, 4, etc., will P of X be true? So if I plug in 1, is it true? Yeah, 1 squared bigger than X. If I plug in 2, is it true? So my question, is P of X true for all X in Z plus? What do you think the answer would be? Yes or no? Back to you. If I plug in any X here, will this be true? I expect answers. We're not going to be working. If you guys do not reply to everything, it's not going to work. Yes. Chris said yes. Everybody agree with Chris?
Yeah, that's true. Sorry, I thought it included 0.
No, I omit it. So this is it true, and the answer is yes. Now, of course, that's not a proof the yes. It's yes because we think it's yes. If I want to convince you it is yes, I have to make a little proof. So why it is yes, and slowly we're building up how to prove. But for now, I'll tell you why it is true. Why x squared bigger than x? Okay, one way we can say, I'm taking x bigger than 1. So x is bigger than 1. So if I multiply by x both sides, so that's a simple proof, multiply by x both sides. And because x is positive, I can do that. I can do that because x positive. So I will get multiply by x both sides, and x positive allows me to do this, will give me x squared bigger than x. So that's really a simple reason why this is a very, very simple reason. So this is my P of x. And this is my domain, and this is crucial. Is P of x true for all x in my domain? Yes, because if x bigger than 1, multiply by x both sides, we get x squared bigger than x. However, the minute I change my domain, suppose I take the same predicate, bigger than x, and I take my domain to be the real number, R, and I ask you the exact same question. So now I changed my domain, and my question is the same. Is P of x true for all x in R? So I changed the domain, and now what's really going on? True or false? Is it true for all x in R? What do you understand by that?
False.
Because?
0 exists.
0 is not the right one, because 0 square is 0, and this equality is absolutely...
Oh, equality.
Yes. So we can do better than that.
This includes negative, right? Negative numbers.
Let's try negative. Is it only negative number?
It's fractional numbers.
Fraction, a half. Let's take x to be equal to half, for example. Then if I take a half square, it's 1/4, and it's definitely not greater than a half. Okay, so if I change the domain, I am totally changing the truth value of my predicate, even though my predicate is the same, changing the domain would change its value. So if this one is true for all x, if I changed my domain, is P of x true for all x? No, because as you guys realize, it fails for one x. Therefore, it's gonna fail. Now, since mathematicians don't like to write a lot, they like symbols. For all x in Z, for all x, instead of always writing for all, there is a symbol for that, and it's the A in reverse. And now we're going to introduce those symbol right now. So quantifiers. Quantifiers. So there are two kinds of quantifiers, and we're going to introduce them. So universal quantifiers is the following. We use the symbol upside down A to mean for all or for every. So instead of writing for all, I write the symbol. Now, suppose P of x is a predicate. Remember, predicate, it's not true, it's not false. Predicate is just a sentence. But what does it mean to say that for all x in D, so D is a domain, the domain is important, is true if whichever x in the domain, if I plug it in here, I will have a true statement. If P of x is true for all x in D. So a statement like this is true if whatever I put in here, I will create a true statement. What does it mean to be false? It's false if P of x is false for at least one value in the domain. If one value in your domain will make P of x false, the whole statement here is false statement. So P of x by itself is not a statement because there is a variable. But when I put a quantifiers in here, now I am creating a statement because I'm creating a sentence which is true or false. It's true if any x in here will make it true. False if one of them make it false, the whole thing is false. Okay, so that's our first quantifier called the universal quantifiers. Now, there is another one, okay, called the existential quantifiers. Because sometimes some sentences are true for some x and false for others. And we want to express this idea. So existential quantifiers. The symbol backward E, if you want, mean there exists at least one. Okay, that's what this means. Now, suppose you have a predicate. It means a sentence that have a variable x. And a domain. It means we're interested, all my x's are inside this domain. Then the statement that exists x in the domain such that P of x. So this read, sometimes they put this, whatever, comma dot, semicolon, or sometimes we just write it like this. There exists x in the domain such that P of x. So this statement is true if there is one value that makes it true. So if you can find one x that makes this true, it means this is true. How could it be false? This is false if no value of x will make P of x true. So it's false if P of x is false regardless what x is. All right, so those are the two quantifiers that you will use basically as far as you are doing math for every that exists. Okay, so I repeat, P of x by itself is not a statement because it's not neither true nor false. When I tag a quantifier to it, then I make it into a statement. It means it has a value, true or false. True if one x make it true, false if every x make P of x false. So let us do three small exercises so we can have You can practice this idea a little bit. So I'm going to give you some statement, and my question to you would be true or false. And they are simple because that's what we can do at this stage. Okay, so please, as I move the paper, let me know if it's all right or not. So now the question is, find the truth value of each of the statement below. So I'm going to write statement, and you have to tell me true or false, right? And we're going to justify. So for all x in R, I'm specifying my domain now. For all x in R, x squared is positive. Quickly, true and false, or false, because now I'm creating a statement. This one should have a value. True or false, very quickly. Very quickly. False. Peter says false. Peter has to justify. What does it mean, false? What does it mean, false? For all x in D, P of x is false if it's false for at least one value. So if you tell me false, you have to give me a value of x in the domain that makes it false. So I go back. If you tell me false, you give me the value in the domain that will make it false. If you tell me true, you tell me why it is true. Back to you. Oh, I misread it. That's okay. So true or false? Absolutely true. Because no matter what x is, no, so my domain is the real numbers. So now we're being very precise with the domains, not the complex numbers. They are the real numbers. So absolutely true, because if you take any number, you square it, it has to be a positive number. Okay. Another one. However, the one that you had on your quiz, for all x in R, x on your homework, x squared strictly positive. Again, my domain are the real numbers. So now there is no more confusion. Is this true or false? Quickly, according to our definition. This is false. False because when you say false, because you have to give me at least one value for which it is false. You can take x equal to 0, then, so this is my P of x here. So take x equal to 0, then P of 0, which read 0 larger than 0, it's absolutely a false statement. Okay, so when we say false, we have to be very precise. All right, two more. Again, they are simple because we don't know how to prove yet, so I have to give you simple problems. For all x in z plus, now z plus is 1, 2, 3, all the integers, 1 over x strictly less than 1. True or false? So remember my domain. Always I'm working within my domain.
That's false.
It's false because
X can be equal to 1.
x can be equal to 1. And then if this is my P of x, then P of 1 will read 1 over 1 strictly less than 1, which is a false statement. Okay. Now, what if I change a tiny bit? 1 over x less or equal to x. True or false?
True.
Because
it's going to be either 1 or greater, or sorry, or 1 or less rather, because one is the greatest fractional number that you can create out of two integers.
X is bigger or equal to
Two
1.
positive integers.
Right. X is bigger or equal to 1, and X is positive, and always the positive play a role, means 1 over it will be less or equal to 1. Absolutely correct. All right, two more, and then we proceed. That exist in X in R such that x squared equal to x, true or false? Now it's an existence problem. Existence is true if. True or false?
It's true.
Because.
Because if you insert either the value 0 or 1, they both equal the square of 0 or the square of 1 equals 0 or 1.
Absolutely true. I don't need 2. I need 1. Because take x equal to 1, then p of 1 will read 1 squared equal to 1, which is true. Okay. My last example, there exists x in Z. So watch the domain such that 2x plus 1 equal to 0. True or false? Okay, Peter gave me bills. Whatever you give me, you have to justify. Okay. All right, threshold, absolutely correct. So you can find in x such that 2x plus 1 equal to 0, and everybody, false, because the only value that makes 2x plus 1 equal to 0, the only value, there is only one, is x equal minus a half, and minus a half is definitely not an element of Z. Okay, so only one number make it true, which is minus a half, which is not a Z, and my domain is in Z. It means no matter what x is, if you take any x in Z, no matter what you take, this term will have to be different from 0. Okay, so that's false, because no matter what x is, it has to be different from 0, because the only one that makes it 0 is minus a half. Okay, so of course we're gonna do a harder problem, but for now we just understand the concepts, and later on when we have more tool in our hand, we will start taking harder situation. Now the negation. Whenever we study something, at least for now, we're gonna learn how to negate it. So what is the negation of a statement? So before we take the rule, remember the negation should capture in it exactly when my statement is false. So when we're negating a P or Q, when we negated that, actually we ask ourselves, the negation should reflect when is P and Q false. So the negation should be true when P and Q should be false. That's what the negation, it captures when our statement is false. So now, if I want to negate a statement like this one, how can this be false? What caused a statement like for every x in R, x squared positive to be false? I want to analyze this. What caused this to be false? Cause it to be false is that exists something in the domain that make this statement false. So what caused the statement to be false is the existence of an element in the domain that makes the P of x false. It means the existence of something in the domain that make the negation, if you want, of P of x to be true. So what caused this to be false? So the negation should capture how my statement is false. So what's the negation of the statement? The negation should reflect why the statement is false. The negation of it, why the statement is false, because you can find an element in R, that's the domain, that makes this actually false, because I can find this such that x squared is negative or equal to 0. Okay, so what caused this false is because I can find an element that make this false. And this will actually motivate the negation of a quantified statement in general. So let us write them down. What is the negation? You have a quantified statement for all x in D, P of x. The negation should reflect how can this be false. It's going to be, it's false if we can find x in D such that P of x is false. P of x is false. It means the negation is true. So the negation of every x is actually that exists in x. So the way we negate for every if by that exists. And actually it makes sense because for every is false if P of x is false. It means if non-P of x is true for at least one value. It means if you can find a value such that non-P of x is true. Now, what's the negation of that exist? So now I'm going to reflect how can that exist be false? This could be false if every x make this false. This is false, so the negation should reflect that. So the negation is for all x in D, this is false, it means its negation is true. Okay. Absolutely, extremely important ideas. Okay, so the negation of that exists is for every x non-P of x. Be very careful, it's not P, it's for all x non-P of x. All right, so let us negate quickly, and because I want those to become a second nature to all of us. So negate. So this is my P of x in here. And that's, of course, my domain. So now I need to negate for all x in R, x squared bigger or equal to x. So what's the negation of that? This is my P, very clearly. So the negation is for every that exists x in R. That's the domain we don't touch, such that non x squared larger or equal to x. But of course, we don't keep non because we know how to negate this. It means I can find x such that x squared is strictly less than x. Okay. Now let us, of course, note, if my original statement is true, my negation has to be false, because that's really what the negation, it reflects when my problem is false. If this is false, this has to be true. If this is true, this has to be false. There is no question asked. If I have both of them true, I'm doing something wrong along the line, because the negation is capture in it all the possibility that my original statement is false. So now this one, we know that it is false because my domain is R. This one, of course, it is true because the reason this is false, because I was able to find an X that make the statement a false statement. All right, 2. You guys do it in front of you very quickly, and then you tell me what you got. Okay, you get 1 minute to do that because I think those are not hard. Okay, who's ready? Who's ready? Just say it in words. Emily? Emily, are you there?
I was still writing it down, but I think it would be there exists an X, or not there exists, for all X, in R, such that, would it be
No,
x
no,
squared?
No. Let me comment immediately. For every, you don't say such that. Okay?
Oh,
The
sorry.
Such that is, you don't have to be sorry. No, never say that. The such that comes after that exists, so it makes sense. That exists in X such that satisfy this condition. For all X in R, then you say what should happen. Okay, keep going.
Would it be x squared is not equal to x?
Absolutely. So it's the
Okay.
negation of X squared equal to X, which is for all X in R, X squared is different from X. Okay. And now, just to check, this statement was true, right? Because you guys gave me X equal to 1. And this is have to be false, because that's what we are really telling you. I'm telling you that I'm capturing, how could this be false? It cannot be false, because this tells you that for all X in R, X squared different from X. Of course, this is false, because we were able to find one that satisfied. For all X in R, X squared. I'm not following. Okay, yeah. All right, now the last one. I want you to negate. So first we have to make sure what's our predicate. That's my predicate. I always focus on it because I want to know, be sure what I'm doing. So again, you guys have a minute to negate. Okay, everybody, for all n is prime or n, absolutely correct. So let's negate. So first, this will go for every n in Z. The negation, and comma, the negation of, sorry, this is not needed. The negation of n is prime and n is even. Now I zoom in. For all x, I meant for all n in Z, comma, so sorry, for all n in Z, n is not prime, or n is not even, that is n is odd, is not even. Okay, so very quickly now, true and false. Is my original statement true or false? Quickly, my original statement, true or false? True, because we've done this before. N equal to 2. True, that exists. Take n equal to 2, that's prime, and that's even. Of course, this has to be false, because it tells you that given any n, either it's not prime or it's not even. That's false, because n equal to 2 satisfies both conditions. We're going to do four more examples, but now it's a little bit of in English. I'm going to give you an English sentence in English, and you have to actually negate it, okay? So here is the question. I want you to introduce a domain. I want to introduce a predicate. I want you to write the sentence as a quantified statement, and then I want you to negate, okay? So I will guide you through the first one, what I'm after, and then you guys will do the rest. So all mathematicians wear glasses. Okay, so what do I mean by introduce domain and predicate? It means, what am I talking about here? So the domain, I can say it's all mathematicians, since that's what I seem to be including in my sentence. All mathematicians, okay? My predicate, so P of X, it means here X stands for a mathematician. That's what X stands for. P of X is X wears glasses. Okay, so my sentence becomes very clear. Now, and then I want the sentence to be written as a quantified statement. Okay, so as a quantified statement, how you're gonna write it? For all X in D, all mathematicians wear glasses. So that's the sentence written as a quantified statement. Okay, and now I want the negation as a quantified statement and then the negation in English. So let us negate it. Okay, now the negation is easy because I know exactly what I'm talking about. So the negation would become there exists X in D such that none P of X. And finally, the negation in English. There exist all that exist. A mathematician that does not wear glasses. Wear glasses. Okay, so all, of course, gave it away. All mathematicians, it means there exists a mathematician, wear glasses. There exists a mathematician that does not wear glasses. Okay, so let us go through in this one it's easy, true or false. If my initial statement, is my initial statement true or false? All mathematicians wear glasses. True or false? What do you think? You know a bunch of them in the math department.
False.
False. There exists a mathematician that does not wear glasses. Of course, this is true. I mean, we are negating that. All right, now very quickly, I want you to do number 2 for me. Let the domain be the most logical one. Like in this problem, I want the domain to be all the roses in the word. Okay, who's ready? Who's ready? Nick? Nick Salas? Quick, who would like to negate the sentence for me? Rachel?
Would it just be the same as the last one, that there exists a rose that is not red?
Yeah, there exists a row that's not red. All that exist arrows, red, that's not red. Okay. All right. Number 4. All students in this class, speak English and no calculus. Okay, I'm definitely assuming that's a true statement. Negated.
There exists at least one student in the class who does not speak English or does not know calculus.
Right. That exists for all students. There exists a particular student. That's really what we mean. A particular student in this class that doesn't speak English. Or, and we negate or doesn't know calculus. Speaks English, so all students in this class, that's my predicate. My domain, student in class. My predicate, X, speaks English and no calculus. My quantifier is for all. Right? So 2 more questions along the same line. Okay. Right? Okay. So let me call this is 4. There is a student in this class that speaks Urdu. May I assume the statement is false? Does any of you speak Urdu? I don't think so. All right. There is a student in this class that speaks Urdu. I want the negation. What's your domain? What's the predicate? What's your quantifier? And then negate. And whoever ready, let me know. Okay, all students in this class don't speak Urdu. Okay, that is, or you can hear every student in this class doesn't speak Urdu. Okay, now, you guys agree? That is, every student in this class, that's the domain, I'm not touching the domain, speaks Urdu, doesn't speak Urdu. Every student in this class doesn't speak Urdu. Now, sometimes students would write the same thing in a different way, and let's see if they are right and make sense of it. So suppose I write, no student in this class speaks Urdu. Does this mean the same thing? No student in this class speaks Urdu. I would like to make sense out of that. What does this mean? No student in this class. So basically I'm saying no X in the domain, no X has the property, no student speaks Urdu. What does this sentence mean? It means whichever student you give me, the student doesn't speak Urdu. It means every student doesn't speak Urdu. Okay, so what does the statement no student in this class speaks Urdu can be written? So let's write this down here. Sometimes we have the following sentence. No X in D such that P of X. What does this mean? in general. So no x in a certain domain such that p of x. This means that given any x in the domain, non-p of x. Okay, no x such that p of x, it means no matter what x is in D, no matter what x in the domain, non-p of x. So in other words, this is basically the negation of that exists in x in D such that p of x. So a lot of time we will encounter statements that say, okay, no x have this property, but this means that every x does not have this property. It means basically we're negating the existence of something that have this property. So with this, I will finalize with this, not finalize, sorry. I will consider the following problem. There is no real number such that x squared equal to 2. And my question is negated. Okay, no real number have this property. Okay. Who's comfortable negating this for me? Anybody? So there is no real number such that x squared equal to 2. What's going to be the negation? What does this mean? Given any real number, x squared is different from 2. Huh? Do you agree with him? Is this the negation? There exists no number such that x squared equal to 2. Is this the negation of that? Nick, are you giving me the negation? What do you understand by this sentence? There is no number such that x squared equal to 2. What do you understand by that? Given any x in R, x squared is different from 2. That's really what it means. That's not the negation. There exists no number such that x squared equal to 2 means every real number does not satisfy. X squared is different from 2. So its negation is going to be basically there exists a number such that x squared equal to 2. Okay, so let us repeat. There is no x that satisfies this property means every x that's me, that's not the negation, means every x in the domain doesn't satisfy it. Means it's basically you are negating the existence of something such that p of x. So no number satisfy x squared equal to 2. The negation is there is a number that satisfies x squared equal to 2. If I tell you there is no student in this class who is over 60 years old, is this a true statement or a false statement? Suppose I give you no student in this class is over 60. I'm assuming this is absolutely a false statement. So what am I telling you? No student in this class is over 60. Okay, this is equivalent to say every student in this class is below 60. So no student in this class is over 60. That's a true statement, of course. No student is over 60. Means every student in this class is below 60. So the negation, how can this be false if there exists a student? So the negation is there exists a student which is over 60. So I repeat, no student in this class over 60. That's a true statement because the only way it can be false if there exists one who's over 60, which is not the case. So the negation of no student is over 60 is there exists a student over 60. Can you go back to what you have? I want to make sure I have it copied correctly. Is this one Nick you're looking for? Yeah. No x as at p of x, it means you negating the existence of x such that p of x. Try to think through it. No student is over 60, it means you're negating the existence of a student over 60. So the negation of no x is that exists in x. The negation of no x is that exists in x. Okay, I wanted to think about that because usually students stumble with this no. So I'm gonna give you actually some worksheet for next time that you can do that. All right, so quantified statement. So we have a predicate and we define the notion that what does it mean for all x in D, p of x, it means this is true for all x. And that exists in x, it means that this is true for some x. Now, some predicate involve more than one variable. So I can have the following predicate. I can say, let us say, p of xy is the predicate x less or equal to y. Now I have two predicates, x and y. So not only one. So that's a predicate with two variables. So if I want to know whether, so what's p of 1, 2, for example, it's 1 less or equal to 2, which is like a true statement. P of 2, 1, 2 less than 1, which is a false statement, and so on and so forth. Now, when we have two predicates, we have an issue. And how can we make a predicate with two variables into a statement? So this is not a statement, of course, but how can we make it into a statement? So I will start by an example as usual, and I want you to try to make sense out of it. So we call this idea, the idea of nested quantifiers. Nested quantifiers. So I'm going to write a sentence for you. Okay, and I want you to write it to me in English. So I'm going to write it, I'm going to write it in words, and you have to write it to me in English. So let us see. Suppose I tell you the following. For every real number y, for every real number y, there is a real number x such that x strictly less than y. Okay, I want you to write it for yourself, and I want you to read this. We're gonna, so for every real number y, there is a real number x such that x is strictly less than y. I want you to write it as using quantifiers. And then, is this statement true? Is the statement false? What makes sense out of it? All right, Peter wrote it. For every real number y. So we always read from left to right. Left to right. We read verbatim from left to right. For every real number r, okay, there is a real number x. left to right, there is a real number x. So I'm reading and writing. I'm actually writing what I read. There exists a number x such that x is less than y. Now, here is my question. So do you think the statement is true or false? Just your hunch. So for every number y, I can find an x so that x is less than y. Now, I will define what it means by true or false, but now just for us, do you think the statement is true? And what do you understand by this statement? What do we understand by this statement? Okay, Peter, tell me it's true. Why it is true? What do we understand by this jumble mumble of quantifiers? It means the following. For every y in R, no matter what y is, I can find an x that has the property that x is less than y. Means no matter what y is, you can give me an x such that x is less than y. That's what it means. So is this true or false? Let us play the game. If I give you y equal to 1, can you give me an x that makes this property true? Okay. If I give you y is 1, can you give me an x that makes this true? Very quickly. If y is 1, I don't know, give me x to be 0. X is less than 1. If I take y equal 15, can you give me an x that makes x less than 1? Okay, if y is 15, I want something, x equal 14. So what does this mean for this statement to be true? It's true, it means that if I give you any y, regardless what it is, can you give me an x? And this x actually gonna change with the y that makes the statement true. So that's what it means for the statement to be true. Now, when we have two predicates, I need two quantifiers, because if I don't put any restriction on y, and I give you there exists an x in R such that x is less than y, I don't know what is y in this case. Okay, so what does it mean for a statement of the following form to be true? So definition. And then we go back to the same example. Suppose P of xy is a predicate. It's just a sentence that has two variables. And big X is the domain of the variable X, and big Y the domain of Y. Okay, that. The statement. For all y in Y, there exists X in X such that P of xy is true. A statement like this is true if, okay, read it. If you read it, you understand if given any y in Y, if for every y in Y, we can find a particular X we can find an X in X, and here you can put with parentheses, X of course changes with Y. So when Y changes, X will changes. We can find X in X such that P of xy is true. Okay, so a statement for all y in Y. There exists in X such that P of xy, that's a true statement if no matter what y you give me, I can give you an X that makes the statement true. You change your y, fine, I can give you another X, and so on and so forth. Is false. What does it mean for it to be false? If So the statement is false. If, okay? How can this be false? So it's true if no matter what y, I can find an x that make this true. So how could this be false?
You move your paper to the side so I can see like the statement. Thank you.
This way?
Yes, thank you.
Okay. What does it mean to be false? Who would like to tell me what it means? Of course, using what we did before. For all y, no matter what y is, I can find an x. How can this be false? And the way I want you to think about it is like, that's where the word nested coming from. So true is no matter what y is, I can find an x. It's false if, anybody would like to give it a false if we can find a y, if we can find a y, that makes this statement false. Means we can find a y such that, how can this be false? We can find a y such that no matter what x is, p of xy is false. Okay, so this statement is false if I can find one y that will make this statement false. I can find a y such that no matter what x is, no matter what I put in for x here, p of xy is a false statement. Okay, and that's where we're going to take you from next time, and we're going to work over, of course, a lot of examples to understand this concept. All right, for Wednesday, I'm going to put a small worksheet on Brightspace about predicate, like the one we did in class. I will answer your question next time, and then we're going to do what we call nested quantifiers, which is when we have some predicate that depend on two variables, and this is going to imply I need two quantifiers to be able to work with. All right, and please start your homework. All right, any questions? Anybody has any questions? Because they're too quiet. All right, so I have office hours. If you have any questions about your homework, about the grading, please let me know. Okay, and bye for now.